Okay, here are some general results in the context of growth of functions. For n greater than or equal to 1, we know that n is always smaller than 2 to the power n. By definition, this means n, the function n, is big O 2 to the power n. And if you take the logarithm of both sides, well, since a logarithm is a monotone function, the inequality will be kept. So log n will still be smaller than log of 2 to the power n, and log of 2 to the power n is equal to n times log of 2. And log of 2 here can serve as the constant c. Therefore, you see, for n greater than or equal to 1, this inequality tells us that this function log n is big O this function. Log n is big O n. This means the function n upper bounds log n asymptotically as n goes to infinity. Another result is n factorial can be written as 1 times, 3 times, 2 times, 3 times, 4, etc. up to n minus 1 times n. This is obviously smaller than n times n times n, etc. By replacing each of these with n, I obtain a larger number, obviously, and therefore n factorial is big O n to power n. Again, if you take the logarithm of both sides, you've got log n factorial is big O n log n. And in general, here's a summary of some elementary functions. 1 or any constant is big O n, and log n is big O n. In fact, 1 is, or any constant, is also big O log n, or any function that grows with n, because 1 or any constant is a constant, so it doesn't actually grow. And n is a big O n log n. N log n is big O n square, so n square grows faster than n log n. And n square is big O 2 to the power n. This is significant now. N square is a polynomial, and 2 to the power n is an exponential function, so its rate of growth is larger than the polynomial. And in general, if a is less than or equal to b, we can say that a to the power n is big O b to the power n. And again, in general, 2 to the power n is big O n factorial, so n factorial grows faster than the exponential. And as we have just seen, n factorial is big O n to power n. So we have sort of a hierarchy between these functions. So this is useful when we talk about analysis of algorithms in the context of performance. For instance, we have talked about the number of operations required to be executed to conclude the algorithms. For instance, recall the linear search. We need 2n comparisons at first, n being the number of values in your sequence to be searched, and n comparisons on the average. Okay, and in this case, we say that linear search has big theta n, worst case, and average case complexity, because, well, 2n and also n are big theta n. They are polynomials, so they are big theta n. Also recall binary search. We need 2 times log 2n comparisons, log 2n plus 3 assignments, so memory access and modification, log 2n additions and divisions. If you remember, this is for computing the middle index, left plus right divide by 2. So division comes from that divide by 2. And this is the worst case scenario. If you add them all up, the worst case complexity of the binary search turns out to be big theta log n. Here, the convention is writing log n instead of log 2n, because, well, it doesn't really matter. Log any base, log n, or let me just use log m n, is essentially log n divided by log m. Whatever base you think of here, it could be a natural logarithm or a base of 10 here, doesn't really matter, because this is a constant and this becomes the function. So we usually use log n instead of log 2n. Okay, so we don't really indicate the base because it's irrelevant. All logarithms, they have the same growth rate. So when you classify algorithms, you look at usually the worst case performance or the average case performance. So if it is theta 1, it's constant time algorithm, it's the best case. In fact, if you have such an algorithm, that's great. But sometimes you make up for it using more space in memory. Big theta log n is called logarithmic, as the name suggests. Big theta n is called linear. So here, of course, your actual number of executions could be 78n plus 942, or it could actually be 3n plus 1. So both of these are linear, right? So they have linear complexity, okay? It could be this one or this one. So in practice, this one, of course, is going to require more time. However, we are not interested in the actual specific time, the amount of time the algorithm requires. We are interested in how it behaves as the size of the input grows towards infinity. So these are linear, so these are good. Okay, so linear complexity is not going to blow up when the input size increases. N log n is called linear arithmetic, and now you have well, this shouldn't be here. Theta n to the power b, in general, for any b value here, we call this polynomial. Obviously, it could be n to power 2, n to power 5, n to power 3, n to power 8, but they are all polynomials. That's the main thing. And of course, a linear function is a special type of polynomial, so you can also count that in polynomials. And after polynomials, it gets fast. So b to the power n we call exponential complexity, and n factorial is obviously factorial. So up to this point, if any algorithm belongs in this partition, that's a good algorithm essentially, because we call those tractable algorithms, polynomial or better. And these ones, exponential or factorial or even worse, these are problematic because they require a lot of runtime, especially when the input grows.